Let me ask you something. Have you ever stared at a problem that's so ridiculously complex with so many possible answers that finding the single best one just feels impossible? Well, today we're going to crack open a fascinating algorithm that tackles these exact kinds of problems, and it does it by borrowing a secret from, of all places, an ancient blacksmith's forge. So to really wrap our heads around this, let's start with a classic. It's called the traveling salesman problem. The goal sounds simple, right? You've got a list of cities, and all you have to do is find the absolute shortest route that hits every city just once and then brings you back home. Easy peasy. Except it's not. The complexity just explodes faster than you can possibly imagine.
For a salesman who only needs to visit 20 cities, just 20, the number of possible routes is, well, it's that number on your screen. That is 2.4 quintillion. It's a number so big it's hard to even process. Think about it this way. If you had a supercomputer checking a billion routes every single second, it would still take over 77 years to get through them all. The scale is just insane.
So that brings us to the big question, right? When you're dealing with a number of options that massive, how can you ever know for sure that you found the absolute best answer, and not just one that's kind of good? Trying to check every single one, what we call brute force, is completely off the table. We need a way smarter approach. Okay, let's think about this for a second. If someone handed you this problem, what would your gut instinct be? How would you start? The most common sense thing to do is to just be greedy. From wherever you are, you always choose the very next step that gives you the biggest, most immediate improvement. You can picture it like a hiker who wants to find the highest point in a mountain range. Their strategy? Always walk uphill. Never go down, just keep climbing. Sounds pretty logical, but it has a huge, fatal flaw.
In the world of computer science, this strategy actually has a name. It's called hill climbing, and, well, it often walks you right into a trap. Let's see exactly why.
So here's the critical part. The hill climbing algorithm stops the very second it can't find a better move right next to it. It takes a look around from its current spot, sees no uphill path, and just says, "All right, I'm done. I've reached the top." But has it really? And this picture just illustrates the problem perfectly. The algorithm climbs the very first hill it finds and gets totally stuck at the top. We call this a local optimum. It's the best point in its immediate neighborhood. But what it can't see, what it's completely blind to, is that a much taller mountain, the true global optimum, is right over there across the valley. And to get to it, it would first have to go downhill, a move that the greedy always go up strategy absolutely forbids. So yeah, the simple, intuitive approach, it fails. It's just too short-sighted and it gets trapped way too easily. We need a way to escape these little hills and explore the whole landscape, but how? Well, the answer comes from a place you would never, ever expect. The solution to this incredibly complex computer problem isn't found in a math textbook. It's found in metallurgy, in the ancient craft of annealing steel. It turns out making a piece of metal stronger and finding the best solution to a problem have a shocking amount in common.
This is the direct connection right here. The folks who came up with this algorithm were literally inspired by a physical process that's been used for centuries to create strong, stable, and, well, perfect crystal structures in metals.
Let's break down how it actually works, because this is the whole key. First, you heat the metal way up. This pumps the atoms inside with a ton of energy, letting them jiggle around and break free from their rigid spots. They're just exploring all kinds of different arrangements. Then, and this is the most critical part, you cool it down really slowly. This gives all those atoms the time they need to find their perfect positions, settling into a highly organized, low-energy state, a perfect crystal.
Okay, so how on earth do we translate this physical idea of heating and cooling into an algorithm that can solve a problem? Well, this is where the magic really happens.
We simulate the whole process. When the temperature is high, the algorithm is energetic, it's chaotic, it's exploring the entire landscape of possible answers. And here's the secret sauce. It has a pretty good chance of accepting worse moves. It's willing to go downhill for a bit just to see if there's a bigger mountain on the other side. This is exactly how it escapes the trap that doomed our hill climber. Then, as the temperature slowly goes down, the algorithm gets pickier and pickier, until finally, at the very end, it's only accepting moves that make the solution better. This whole controlled cool-down process has a name. It's called the annealing schedule. And that schedule, how hot you start and how slowly you cool down, is everything. If you get it wrong, the whole thing falls apart. But if you get it right, you can find almost perfect solutions to problems that seemed impossible. And just look at this. This is the visual proof.
On the left, that's what happens with a fast cooling schedule. It's called quenching. You trap everything in a messy, high-energy state. It's a bad solution. But on the right, oh, that's what you get with a slow, patient cooling schedule. The system finds that perfect, low-energy, crystalline state. It's a beautiful, optimal solution. The difference is just night and day.
So you see, the success of simulated annealing isn't just about the cool idea of temperature. It's really about the art and the science of designing the perfect cooling schedule for whatever problem you're trying to solve.
And the results are just staggering. By allowing for that initial period of messy, random exploration before it slowly zeroes in on the best possible area, this algorithm can solve huge problems, like this wild 3D version of the traveling salesman, finding a path that a simple hill climber could never, ever dream of finding. And this idea isn't just for some abstract math problem. It is used everywhere, for some of the toughest challenges we face. Things like predicting how proteins will fold, which is huge for developing new medicines. Figuring out the absolute most efficient schedules for giant factories. Designing the intricate computer chips in our phones. It's even a major tool in AI and machine learning.
It really leaves you with a pretty cool final thought, doesn't it? This incredibly powerful idea, inspired by a blacksmith's forge, shows us that sometimes to find the most perfect, ordered solution, you have to be willing to embrace a little bit of chaos first. What other impossible problems out there are just waiting to be solved by first getting things heated up and then patiently letting them cool down?